Hello everybody, Miss Labiniak here, and I would like to quickly overview a few of the ideas that you'll encounter in tonight's reading. Tonight's reading is all about modeling motion, and the first idea that you're going to encounter is that of the motion diagram. Now, a motion diagram is exactly what it sounds like. It shows an object and its motion over some period of time. And the important thing about a motion diagram is that it shows the object at equal time intervals. So in the first case of the skateboarder, you could see it's moving the same distance in each time interval. That's an example of an object moving at a constant speed, and you can tell that right away from the motion diagram. The second diagram, you could see the runner increases the amount of distance she covers in each time. That's an example of acceleration. And then you could see a car that decreases its distance in each time interval, and the motion diagram tells you that object is slowing down. One thing that we do when we're modeling motion is we don't really spend a lot of time drawing the details of the objects because all we really care about where it is in a certain time. And so to do that, we use what's called the particle model, which is really just representing the object as a dot and labeling the time that goes along with each dot. So the runner would just be a dot that got further and further apart, and the car would be a dot that got closer and closer together. Another important concept in the reading is the idea of position. It answers the question, where is it? Position, to really describe it, you need to establish a coordinate system. I know you're all familiar with those. Here we have a number line type coordinate system, has an origin, and it goes in the negative and the positive direction. We usually use X to denote position, especially when we're moving horizontally. Sometimes if we're talking about vertical motion, up, down motion, we'll use the variable Y. The important thing to know about position is it can be negative. The cow is at a position of x equals -5 miles. The car is at a position of x equals +4 miles. And if I had a little house over here, it would be at a position of x equals 0 miles. What's really important when you're talking about position is that you don't just include a number. It's not math, it's physics. So it has a real physical meaning and you need to include the unit. So miles is the unit that we use here. Although when we're doing physics, we often use meters. That's going to be our primary unit of measurement for position. There's also kilometers, there's also centimeters. Those are all metric units, but meters is the one that we use most often in physics. Sometimes when you're studying motion, you want to ask the question, how far did it go? And there's actually a couple of different ways to answer that question. The first is with the idea of distance. Distance in physics is a measure of how much space or ground an object has covered in total. We use the letter D to symbolize distance most of the time, and it's really just overall how much ground or how much space did this object move through in total. And here's a great example to illustrate distance. Here we have an ant that's starting at a position of x equals 40, and it moves to the left to a position of x equals 15. And so it travels to the left a distance of 25 centimeters. After that, it comes back another 15 centimeters to x equals 30, and then it goes back in the other direction again to x equals 10, so it moves another 20 centimeters to the left. In total, even though it did a lot of doubling back and didn't get very far overall, that ant traveled a total distance of 60 centimeters. So distance is overall how much space it covered without really caring about all the doubling over on itself. We do have a word that takes care of the doubling over on itself, and that's the idea of displacement. Displacement describes a net change in position. It's what you kind of intuitively want to think about with this ant. Even though it zigzagged a whole bunch, it really didn't get very far from where it started. And just by looking at the number line, we could see that the ant moved 30 centimeters in the negative direction. And so we would say its displacement is -30. A more formal way to calculate that is with the definition of displacement. Delta x, the change in position, is going to be equal to the final position, which was 10 centimeters, minus the initial position, which was 40 centimeters. And that gives you the -30 centimeter value for displacement, meaning the ant winds up 30 centimeters relative to where it was in the negative direction. Time is another really important quantity in physics because time and distance allow us to calculate speeds. Time, you can talk about absolute time, kind of what time is it, how much time has gone by since the beginning, or you could talk about time intervals from t equals 3 seconds to t equals 4 seconds. And you might talk about the change in time between two different points. Time can be measured in hours and years and minutes and seconds and days, but in physics, just like we use meters for distance, we use seconds for time. Finally, we want to know how fast something is going. The quantity that answers that is speed. And there's a couple of, speed is actually can get quite complicated, but just in a nutshell, speed is a measure of how much or how far something moves in a given amount of time. It's the total distance traveled divided by the time interval. And so we could see here for the car that this car is traveling about 40 meters every second. So this car has a speed of 40 meters per second. And since it's a distance over a time, its units are meters per second. If we look at the bicycle, we could see the bicycle is moving slower. It's only traveling 20 meters per second. And so speed really is a measure of how fast something is, how much distance it covers in a given time. Now, this technically is only the definition of speed if your speed is one value, if you have a constant steady speed, which is true in both of these cases. If we were like the runner or the car in the earlier examples that were getting faster or getting slower, we could still use this equation, but we would have to be a little more specific and call it our average speed because the speed would be varying throughout the situation. And finally, there's another quantity you'll encounter, which is called velocity. And you probably use speed and velocity interchangeably your whole life. However, they're different, and they're particularly different in physics. Velocity measures not only an object's speed, but also its direction. So it answers the question, how fast and which way is it going? So here's an example of a bicycle. Both bicycles, you can see by inspecting them quickly, are traveling 20 meters every second. This one is starting over here and traveling to the left, and this one is starting over here and traveling to the right. They're both traveling 20 meters per second, but bike one is traveling to the right, and bike two is traveling to the left. And to denote the leftwardness of that, we would represent that by a negative, since left on our coordinate system is negative. And so even though these objects have identical speeds, they're both traveling at a speed of 20 meters per second. They're traveling with actually opposite and very different velocities, and that is an important thing to keep in mind. One way to think about it is that speed is the absolute value of velocity when you're talking about straight line motion. Another thing to keep in mind, and this is just a quick preview, you can talk about your average velocity, and there is a formula for that that we'll learn, and it is your displacement over your time. So even though speed cares about your total distance that you travel, velocity cares about your displacement because those are actually both directional quantities when you think about it. Okay, so that's it for now. I hope this gives you a little overview of the reading and helps you make sense of it on your own, and we will see you at the end of the week.